Hello everyone. So today we will be discussing slab base, which is a part of design of compression members. Now, before going to the topic of slab base in details, let us try to revise the load transfer mechanism. You see, essentially, if you remember the configuration, the load transfer mechanism in the system, it starts from the roof covering, okay and then through the purlins or whatever may be the system, the load gets transferred to the skeletal structure. And skeletal structure may be the like frame, okay frame beam or the truss system. We're not talking about the columns. First of all, it goes to the frame beam or the truss system. After that, it gets transferred to the vertical members. And what is our objective? Our objective is to transfer the entire load to the ground below. And to do that, we need to support these vertical members or the columns, to the foundation system. And most of the time, the foundation system is made of concrete. So since the foundation system is made of concrete, what happens is that we need to create an interface, which is important. We need to create an interface between the steel column and the concrete foundation. Okay, now suppose you have selected an I section. Okay, and this is the foundation. This is the foundation, and the foundation is made of concrete. And the column is made of steel. This is the top view. Column is made of steel and the foundation is made of concrete. Now if we connect the steel column directly on the concrete foundation, if we connect the steel column directly on the concrete foundation, the whole thing can punch through. The whole column can punch through the concrete. The reason is that the load acting on this will create a stress which will be very high, because the area of the I section is very less. You know that stress is equal to load by area. So if there is a load, then load divided by this area is very less, so obviously stress will be very high. So due to the stress, there is a probability that the column will punch through. So therefore, what we try to do is we distribute the load instead of concentrating it on the uh, area of the I section. We try to distribute the load over a larger area. Instead of concentrating the load P over this area, over a smaller area, because smaller area will be giving higher stress. So instead of concentrating the load P on a smaller area, we try to distribute it over a larger area like this. And for that we use another steel element, which is called as the base plate. So that is our primary objective, to increase the area. Instead of distributing the load P over a smaller area, we are now distributing it over a larger area of steel, which is why we are using a steel base plate. It is a plate which is provided at the base of a column. It is provided at the base of a column. And that's why it is called as a base plate. Now if you try to uh, look into the section from either this side or this side, how will it look like? So it will look like this, isn't it? If you're looking from this side or this side, this is the concrete base, this is the base plate, and this is the column. I section. These are the flanges. Okay, this flange will be this one and this one. This is the web. So this one is the web. Okay, so that will be the view that you will get. Now, when we are told to design the base plate, we are actually concentrating on the dimensions of the base plate. Okay, that means we are talking about the length, width, and thickness. Length, width, and thickness of the base plate. So now we will be discussing one problem, and along with the problem, we will try to look into the various concepts in the design of a base plate. So in this problem, a column is given to us. Okay, the column is ISHB 300 at 63 kg per meter. Okay, 63 kg per meter is the weight per meter of the steel element. Okay, and the factored load is given to us is 1000 kilonewton. Okay, and the material properties are Fe410 and M25 for concrete. Now, first of all, what you have to do is you look for this in the steel table. Okay, and write down the area, then the all the dimension values of the web, the flange, okay, the height of the section, all those things you write it down. Moment of inertia values also you write it down. Okay, so these are the values of the dimensions. Okay, and also write down the values of the moment of inertia. So these are the moment of inertia for the um, and radius of gyration values for both the axes. So after writing these values, our first step is to find out the bearing strength of concrete. So for finding the bearing strength, the formula is this is a very important formula, and it also like it comes in the examinations also. Okay, so now you find out the bearing strength, how much it will be. So this will be the bearing strength of concrete. Okay, so now you see here uh, we have got the dimensions of the column. Okay, we have not yet started with the base plate. Now this is the amount of stress that the concrete can take. Okay, so what will be the area required for the base plate? You see here, the area required will be load divided by this stress. Okay, so find it out. So how much it will be? Isn't it? So area required for the base plate is the load divided by the bearing strength of concrete that we have got. It is 88.89 into 10 cube mm square. So now we have to first find out the dimensions of the base plate from this area. Okay, so how will we do it? First of all, let us draw the diagram. Okay. Now just you mention the values of H and BF in the column section. Okay. All right. So this is the dimension of H and BF. Okay, from the steel table. Okay, like values of H and BF from the steel table which we have got. Okay, we have mentioned it here. This is H. This is H for the steel column, and this is BF for the steel column. And let us consider that this is the base plate. Okay. Now let us since it is this dimension is rectangular, right? 300 by 250, 300 by 250. This overall dimension is rectangular, so that's why we will also take a rectangular base plate. If the dimension would have been square, like 300 and 300, we would also have taken a square base plate. Now since it is 300 by 250, 300 by 250, overall it is a rectangular dimension, so we will also take a rectangular base plate. Now the dimension that we will be taking is for this and this and this. So we will take the dimension in such a way, there is no other specific rule, it is based on our own calculations. There is no specific rule, we have to just take dimensions from ourselves. Okay, so let us assume one dimension which will be rectangular and which will be more than 88.89. Okay, this is the required area, so obviously we will be providing a little more area. So how much shall we consider? Let us consider 400 by 350. So if we consider 400 by 350, this is also a rectangular dimension, and if we multiply 400 into 350, then also we will get an area which is higher than 88.89 into 10 cube mm². Okay, these values are all in mm. Okay, 350 mm, 250, 300, all are in mm. So 400 mm into 350 mm will be higher than 88.89 into 10 cube mm². You can calculate also, you will be able to know it. Now what we will do is we will calculate the offsets, okay, from the edges of the base plate, okay, from the edges of the base plate to these points. Okay, so let us calculate it. So these are the dimensions that we need to find. This one, this one, this one, this one, this and this. Okay, so we have like designed it in such a way that the steel column is in the center of the base plate. This is the overall base plate, and steel column is at the center. Okay, steel I section column is at the center. Now if we want to find out this value and this value, it's very easy. If this is 300 and this is 400 and the column is at the center, this is be 50 and this will be 50. If this is 50, this is 50, overall it is 400, isn't it? If this is 50, this is also 50, this is also 50. Now this is 350, this is 250, so obviously this will be 50 and this will be 50. Okay, it's very easy to find out how it is 50. 350 minus 250, 100, so 50 here, 50 here, because the column is at the center of the base plate. Okay, so now these dimensions are actually termed as A and B. Okay, A and B. Now A and B, A will be the higher value and B will be the smaller value. Okay, sometimes what happens is if this is suppose 420 instead of 400, then what would have happened? This would have been 60 and 60, isn't it? I'm just saying if this was 420 instead of 400, this would have been 60 and this would have been 60. So this is also 60, this is also 60. Okay, and suppose remaining 350 is same as it is, then this would be 50-50. Okay, so in that case A will be 60 and B will be 50. Okay, now here in both the cases it is same, equal, 50-50, 50-50, 50-50, 50-50. Okay, so since both of them are equal, so both of them will have the value of 50. Okay, I'm just repeating once. If this would have been the situation, then A would have been 60 and B would have been 50. In one direction it is what? It is longer, isn't it? So longer value would be A and the smaller value would have been the value of B. But in our case it is 400. So both are equal. So both are 50. Okay, now uh, this is we are done with this part. Okay, so the bearing strength of concrete we have already got. This is what? 11.25 Newton per mm square. Okay, in the previous steps we have already got 0.45 into FCK. Now, if the plate area we have provided is having a higher area, so what will be the new bearing stress on the concrete? Okay, you can write it down. Since we have given a higher area than required, okay, area required was 88.89, we are giving a higher area, so obviously the bearing pressure of concrete will be lower. Okay, so how much it will be? Okay, so it is obviously lower than the bearing strength of concrete. So in that case the concrete is like the whole system is safe. Okay, all right, so we have provided a significantly larger area, so that's why from the bearing pressure, bearing strength point of view, the like the whole system is safe. Now that means the dimensions are okay, 400, 350. So what is the last thing that we need to calculate? It is the thickness. Okay, so for thickness you need to take out your IS code and you go to clause 7.4.3.1. So there is a formula, you write it down. That is the formula for the thickness. So from the clause we have got clause 7.4.3.1, we have got this formula for thickness. Okay, so A we know, B we know. This value we will get from table 5 page 30. Okay, it will be 1.1. Okay, table 5 page 30. Okay, so all the factors are given there. Then W will be this one. W will be this one, and Fy is 250 for if the material is Fe410, Fy will be 250. So now let us find out the thickness. Do it yourself, don't just copy from me. If you find any like confusion after calculating yourself, you can take the reference in the board. So the thickness we have got is that it is 11.75. Now one thing it should satisfy it is that it should be greater than the thickness of the flange. Okay, that is one important condition it should satisfy. So in this case it is 10.6, it is, we have got 11.75. Obviously it is greater than the thickness of the flange, so in this case it is okay. It should always be greater than the thickness of the flange. So now since it is 11.75, let us provide 12. Alright, so this is how we got the thickness of the base plate. Okay, so overall all the dimensions are done. So this is how we design a base plate. Okay, so thickness and the dimensions 400 by 350 into 12, that will be the final dimension. It's one of the easiest topics of compression members, so I hope that you have understood it. So thank you very much.